Okay, we can start. Yeah.
Okay, so welcome to today's colloquium. I'm very happy to introduce Bhaskar Chaudhury from UIUC. Bhaskar did his PhD from Max Planck Institute for Informatics, Saarbrücken. He proved several beautiful results on fair division in his thesis, and one of his papers won the best paper with the Student Lead Author Award at EC 2020. Thanks a lot, Bhaskar, for giving this talk at so early an hour. Over to you.
Thanks a lot, Kavita, for the kind introduction. Don't worry about the hour. It's indeed an honor to give a talk at the colloquium here. And I guess without further ado, I guess I will get started. And as the title suggests, this would be on some existential and computational aspects of the so-called EFX allocations. And don't worry if you don't understand the title, I will explain all of these things in a while. So EFX allocations is a very central concept in fair division. So I would first start by explaining a generic setting of a fair division problem. So typically in an instance of fair division, you have a set of agents and you have a set of items, and you want to divide this set of items among the set of agents in a fair and efficient way. Of course, when I introduce a problem like this, there are multiple layers of ambiguity as to what I mean by the items and what I mean by a fair and efficient manner. But I would, as I said, so these things will become more precise as the talk progresses. So before, I would like to mention a few words about the history of fair division. So if you see this, it dates back to several ancient texts, actually. For instance, first mentions of such problems you can find in, for instance, the Bible, where which involves land division between Abraham and Lot. And I would also say a few words about the protocol that was used here, which is a very common protocol, or rather the canonical protocol that we use nowadays for fair division involving two agents. So Abraham cuts the land into two parts such that he's fine with either of the pieces of the land, and Lot gets to choose whichever is his favorite part. So since Abraham did the cut, or Abraham divided the land, he divided in a way that he's fine picking both of the pieces. And since Lot makes a choice, Lot gets the better of the two. So it's a fair allocation from both of their perspective. And this protocol nowadays, it's pretty commonly referred to as the cut and choose protocol, and I'm pretty sure that most of us might have also used this in our day-to-day life. So despite the problems in this domain being having very early mentions, the proper mathematical study was received since the time of Hugo Steinhaus in 1940s, where he formally introduced the cake cutting problem. And even today, if you see several real life scenarios, like anything which involves a division of labor or division of household chores, or say division of property or of a property of any sorts while dissolving partnerships or while settling divorces or while dividing inheritance, anything of that sort, or even broader applications, like for instance, when managing air traffic and all of these are fair division problems. And if one is actually interested more in the applications and what are the exact fair division protocols used in each of these applications, I highly encourage you to check out this website, splitit.org. So with that, I guess I can start by addressing the layers of ambiguity that I told you in the very first slide. So just to give you an idea of what are the spectrum of problems that can arise. So as I said, so fair division involves division of items among agents, right? So what are these items exactly? So literature distinguishes the items based on whether they're desirable or undesirable. So desirable items are typically referred to as goods, while undesirable items are like chores or tasks of any sort. And it also further makes a difference based on whether the items are divisible or indivisible. So divisible meaning that they can be fractionally allocated, and indivisible meaning that they cannot. For instance, examples of divisible goods can be something like food, while indivisible goods could be electronics, jewelry, furniture, or anything of that sort. And then further motivated by each applications, there are several notions of fairness. And then on each of these settings, like you have several spectrum of problems based on the fairness notion used. So in fact, the literature even considers settings where the set of items to be divided comprises of, say, divisible goods and divisible bads, commonly referred to as mixed manner. For the purposes of this talk, I would stick to mostly these four fundamental classifications, rather the leftmost two, that is divisible goods and indivisible goods, with the more focus on indivisible goods. Anyways, so the one which has been most studied is I mean, most studied in the sense like since 1950s, it has been studied, is fair division of divisible goods. So I would like to say a few words about that right now, and then we would move on to the setting with indivisible goods. So a typical setup of a fair division of divisible goods involves a set of n agents, a set of m divisible goods, and each agent is equipped with the valuation function, which is monotone. So this valuation function captures the utility of an agent to any bundle that can be allocated to this agent. Since the goods are divisible, you can think of each bundle as an m-dimensional vector, where the jth component of this vector signifies how much of good j has been allocated to an agent. So once you feed this vector to the valuation function, it outputs a number which signifies the utility the agent derives when you allocate such a bundle to this agent. Okay, and by monotonicity here, I mean that if you give him allocation, if you give him a bundle which Pareto dominates the previous vector, then the valuation function should not decrease. Okay, so we have agents, goods, and valuation functions. And what is our goal? So our goal is to find an allocation where like you find these vectors x1, x2 up to xn. All of the goods are allocated, and which is fair and efficient. So now I come to the second layer of ambiguity, which was what is this fairness notion? What is the efficiency notion? There are many fairness notions used, but I would stick to one fundamental fairness notion and its relaxations throughout the talk. So which is envy-freeness. So a quintessential notion of fairness is that of envy-freeness. As the name suggests, like an allocation is envy-free if no agent envies the other. So given an allocation, say x1 up to xn, with each xi being allocated to agent I say that an agent I envies an agent I prime if I strictly prefers I prime's bundle to his own. So naturally, an allocation is envy-free if every agent prefers his bundle at least as much as he prefers any other bundle. Okay, so mathematically speaking, for all pairs of agents I and I prime, I have that vi of xi is greater than or equals to vi of xi prime. So I would like to harp a little bit more here that if you look at it carefully, it's a very subtle thing, but it's very important that on the left and right hand side of this inequality, we are using the same valuation function. So we are using the valuation function of agent I. So this means that if agent I envies an agent I prime, then it is primarily because of the bundle that agent I prime possesses. So it's because I finds xi prime to be more valuable than xi. It is not dependent on how happy agent I prime is, meaning that it doesn't depend on vi prime. It just depends on vi. Okay, and don't worry, I would just explain this quickly with an example also. And the notion of efficiency. So efficiency is usually a notion of non-wastefulness. So if you have some set of resources to divide, and if there are some agents who significantly value some resources more than the other agents, I want to make sure that this resource gets allocated to the agents that value it a lot. So again, a quintessential notion of efficiency is that of Pareto optimality, where we say that no agent can be made happier without making any other agent worse. So I say that an allocation X is Pareto optimal if you look at the valuation vector, if it is not dominated by the valuation vector, Pareto dominated by the valuation vector of any other allocation. So there exists no allocation Y where each agent is at least as happy as they were in X, with some set of agents being strictly happier. Okay, so now let me explain both of these concepts with a very small example. So consider this simple setting where you have, say, two agents and two goods, say A1 and A2 and G1 and G2, and the valuation is captured by this matrix, meaning that these valuations would be linear valuation functions, and they would be separable across the goods. Okay, so if you allocate X units of good 1 and Y units of good 2 to agent 1, then the utility would be X times 1 plus Y times 0.1. That's what this matrix means. So here is an allocation where I'm very sorry about that. Yeah. So here is an allocation where you can see that both the agents have been allocated the exact same bundle, right? So clearly this is an envy-free allocation because the bundles are identical. However, this allocation is not a Pareto optimal allocation. Why so? Because, well, if you allocate 0.5 units of both goods, you can see that each agent's valuation is 0.55. However, there is an allocation where you allocate, say, G1 entirely to agent 1 and G2 entirely to agent 2, with both of them ending at, say, 1 and 1 unit of valuation. So this valuation vector, Pareto, dominates the valuation vector of the current allocation. This is a fair allocation, but it is a wasteful allocation. It's not a Pareto optimal allocation. Now consider this allocation where you take the entire set of goods and allocate it to the first agent. Clearly, this is a Pareto optimal allocation because if you want to improve the valuation of agent 2, then you have to take some good away from agent 1 and thereby end up decreasing the valuation of agent 1. So this is an efficient allocation, but it is not a fair allocation. It's extremely unfair for agent 2. So what we want is to guarantee both of these properties simultaneously. And notice that what I said right now can also be generalized to, like, when you have n agents and m goods. If you just want an envy-free allocation, you can allocate 1/n fraction of every good to all the agents. If you just want a Pareto optimal allocation and assuming that the instance is non-degenerate, then you can allocate the entire set of goods to one agent. So it's very easy to guarantee both of these properties individually in the divisible setting, but the challenge is to guarantee both of them simultaneously. So I want an allocation which looks like this, which is envy-free and Pareto optimal at the same time, where you allocate the entire good 1 to agent 1 and the entire good 2 to agent 2. Okay, so is it clear what I want to find? So what is given in the problem and what I want to find? The first question that you usually ask when you define a fairness and efficiency concept is that, is it always possible to be fair? No matter how many agents, how many goods, and what kind of valuation functions I have, can I find an allocation which is envy-free and Pareto optimal? It's not clear from the way I've defined it. And in fact, it is possible for a broad class of valuation functions. And this is one of the most seminal results in mathematical economics. I mean, elaborated in the Nobel Prize laudation of Arrow and Debrew. And this was also found independently by Lionel Mackenzie. So they prove that envy-freeness and Pareto optimality can be guaranteed for concave utility functions. And they show it through the existence of a notion of so-called competitive equilibria in exchange market. It's a very, exchange markets is a very general economic model, and they show the existence of a market equilibrium, and this would imply the existence of envy-free and Pareto optimality. I wouldn't describe what exchange markets and competitive equilibrium means, but I would just like to remark that another fascinating aspect of this result is that markets are inherently decentralized systems where every agent acts according to their own selfish will. And if you want to find an envy-free and Pareto optimal allocations, these are something which are highly centralized concepts. Like you want to find an allocation which satisfies some global set of properties, right? Or it turns out that if you model a virtual market and let the market dynamics, just converge to an equilibrium, then you will get a fair and efficient allocation. So, and this is really fascinating about.
So Bhaskar, you're saying they also come up with an algorithm, is that right? To arrive at the equilibrium?
Unfortunately not. So market dynamics algorithms they came up later in 2010 or in 2000 to 2010 under very specific valuation functions. So this result holds for a broad range of valuation functions, and they prove it through fixed point theorems, and it's non-constructive.
I see. This is what concave valuation functions you're saying.
Right.
All right.
Okay. So yeah, very good point. So as a result, this suffers from the pitfall of being non-constructive because they use fixed point theorem. So as computer scientists, we are more interested in finding the envy-free and Pareto optimal allocation. So there are many ways to do this. So let's look at very simple valuations like linear valuations. Even for linear valuations, can we find allocations which are envy-free and Pareto optimal? You would see that it's very easy to get it. But I would suggest, you can just do it by an LP. You can encode the envy-freeness constraints and you can maximize any welfare function. However, I'm going to show you an approach which also works for a broader range of valuation functions, and it would be very critical because it introduces a very critical concept. So this is another very gem of a result in mathematical economics, which shows that anything which maximizes the product of utilities is also envy-free and Pareto optimal at the same time. This program is famously called the Eisenberg-Gale convex program. So just saying, right now, if you look at the objective, it may not look convex, but product of utilities is essentially sum of logs, which is concave. So it's a concave maximization. It's a convex minimization. So yeah, so this is an Eisenberg-Gale convex program, which says that anything which maximizes the product of utilities is envy-free and Pareto optimal. If you think about it, this is not that surprising because anything which maximizes the product of utilities is naturally Pareto optimal, because if you have a Pareto dominating allocation, it's going to have higher product. Now, why is it envy-free? Well, think of the case when all the agents have identical valuations for now. That means they're actually fighting for the goods. Whatever is the best good for one agent is the best good for all agents. Whatever is the worst good for one agent is the worst good for all agents. In such a scenario, what is the allocation that maximizes the product of valuations? So it's the one that brings the valuations as close as possible to each other, right? So it's trying to get you an envy-free allocation. And this also holds when agents have heterogeneous valuations. So anything which maximizes this will give you a competitive equilibrium. It gives you something stronger than envy-free plus parity optimal. It gives you competitive equilibrium itself. And want to mention that this product of utilities is a concept which also was coined by Nash as a canonical fairness and efficiency measure. Like it's he proves that this is one of like if there are some axioms, and if you want certain welfare function to satisfy these axioms, is a very unique function. So the Nash welfare of an allocation is also defined as the geometric mean, and you would see this concept appearing again and again, even in the setting with indivisible goods. So this is also a Nash welfare maximization problem. So you can also look at it as Nash welfare. So Nash welfare of an allocation is a good way to capture the fairness and efficiency of an allocation. A non-binary way to capture the fairness and efficiency of an allocation. Okay, so what about algorithms? So there are plenty of algorithms which have been studied for the divisible goods case, and plenty of complexity results also. And most of the more interesting questions have been settled here. And I wouldn't cover all of them. I would just mention the two. The first weekly polynomial time algorithm for the linear valuation case was given by Devanur, Papadimitriou, Saberi, and Bazirani, and was later made strongly polynomial by Jim Arlen. So this is just so that you get an overview of what fairness and efficiency means. And now we will kind of move to the indivisible setting, which will constitute the bulk of this talk. So are there any questions till this point?
So I have a question. So what is weakly polynomial and strongly polynomial?
So weakly polynomial, it means that it also your algorithm. So both of them, it needs to be in p space, and the number of arithmetic can also depend on the. So in weakly polynomial, it can also depend on the bit size of your input. So for instance, if your maximum valuation is is v, in a weakly polynomial algorithm, it can also depend on log of v. It's also polynomial. In strongly polynomial time algorithm, it will only depend on n. Let's say n and m. There won't be any dependency on log of v.
In this framework, do people also study, if you have to report your utility function, when do you report it accurately and all of that? Is that well studied?
Yes. There's also some literature on that. I mean, how this is studied. Yeah, it's a very good question. So, but these are also very pretty recent studies by Cole and Getzelis. Yeah.
I see. Okay.
Yeah. Okay. So then let's move on to the next setting, which is fair division of indivisible goods. So now the goods cannot be fractionally allocated, and you would see that this makes things a lot harder. So first of all, let's just get the setting. I mean, it's pretty clear, like you have n agents, m indivisible goods, and now each agent is equipped with a valuation function which acts on any proper subset of goods and maps it to a number, signifying the utility that the agent can derive. And our goal is to find a partition of the good set, x1 up to xn, each xi being allocated to agent I, which is fair and efficient. Okay. Okay, so now let's try to extend the fairness and efficiency measures that we saw in the divisible setting, and let's see what we get. So efficiency notion, we can translate it as this, right? So X is efficient if and only if there exists no other allocation, which Pareto dominates your current allocation. So Pareto optimality can still be used as a notion of efficiency, because Pareto optimal solutions will also exist in the indivisible setting. Can we translate envy-freeness? I mean, yes, we can. I mean, like, look at all pairs of agents I and I prime, and we still insist that we have vi of xi to be greater than or equals to vi of xi prime. But what is the pitfall of this extension is that it will, I mean, if you ask this question, like I said, once you introduce a fairness notion, that can we always be fair? The answer is no. I mean, in a very simple setting where you have just two agents having positive valuation towards a single good, since you're in the discrete setting, this good would be allocated to one of the agents and the other agent won't get any good, and the agent who doesn't get any good will end up envying the agent who is allocated the good. So in very trivial settings, if you insist that you want to get envy-freeness, it may not be possible to guarantee envy-freeness. And this example would show you that it may not be possible to guarantee any approximations of envy-freeness itself. So we should look at, say, relaxations of envy-freeness. So I won't state the relaxation explicitly, but I would try to take you through how we arrive at a natural relaxation. So how do we do this? So recollect that I told you, recollect the Eisenberg-Gale convex program, the Nash welfare maximization, right? So I told you that maximizing the product of utilities is often considered a canonical way to get a fair and efficient allocation. So let's say that you look at the discrete version of the Eisenberg-Gale convex program, where we insist that every xij it's a binary variable. And now let's look at the allocation which maximizes the Nash welfare. Clearly it is Pareto optimal. I mean, that is clear. What can we say about for the fairness? Does it satisfy some kind of a relaxation of envy-freeness? And it turns out that it does. It satisfies what is so-called the envy-freeness up to one good. So let me define this notion here. So also I would like to remark that this notion was coined initially by Lipton, Markakis, Mosen, and Saberi, earlier in 2004. This connection to Nash welfare maximization came later, but I'm just explaining such that you can find how to extend the fairness notion from the divisible setting to the indivisible setting. Okay, so what is this fairness notion? Again, you look at all pairs of agents I and I prime, and right now I say that it is okay if agent I envies agent I prime, meaning that it's okay if vi of xi is strictly less than vi of xi prime, because as we saw, it is unavoidable in certain circumstances. But there must be some good in I prime's bundle, and following the removal of this good, the envy should disappear. So there should be some subset of xi prime of size 1 less than xi prime, which agent I does not envy. So let me make this clear with a small example. So consider the setting. You have two agents and you want to divide a laptop, iPad, and a phone. And valuations are additive, meaning that the valuation on a particular set is the sum of valuations of the items in the set. And consider this following allocation, where you allocate the laptop to the first agent and the iPad and the phone to the second agent. So this is not an envy-free allocation, as you can see that the agent 1 would envy agent 2. But is this an envy-free up to one good allocation? So let's look at it. So agent 1 has a valuation of 10 for the laptop, which is more than his valuation for the iPad, right? Which is 9. In particular, this means that this is more than his valuation on X2's bundle following the removal of the phone. So there exists a good in 2's bundle, namely the phone. In this case, phone or iPad equivalent, it doesn't matter. So there exists a good in X2's bundle, the phone. Following removal of this phone, the envy from 1 to 2 would disappear. And 2 will not envy 1 here. So this is an envy-free up to one good allocation. Okay. And let's consider an allocation like this, where you allocate the laptop and the iPad to the first agent and the phone to the second agent. Clearly, this seems to be a very unfair allocation, and it indeed is. Because if you look at the second agent's valuation for the phone, it is less than his valuation for the iPad. It's also less than his valuation for the laptop, meaning that no matter which good you remove from agent 1's bundle, whether it's the phone or whether it's the iPad or the laptop, the envy still persists. So this is not an EF1 allocation. So is the definition of EF1 allocation clear? Envy-freeness up to one good?
Yes.
Okay.
Any good reason why it's one, some kind of rounding, because it's true for all number of agents and all number of goods, right?
Yeah. So I didn't get the question. So could you
No,
say
is there like a crisp reason why EF1 seems to work? It always exists.
Yeah, I mean, EF1 plus Pareto, EF1 exists, there's a much simpler explanation. So an EF1 plus Pareto optimality exists because this is what you get when you maximize your Nash welfare, the integral version of the Nash welfare. So if this is not true, let's say there is an agent who envies another agent following the removal of any good from the other agent's bundle. You can pick a particular good from the other agent's bundle and move it to this agent's bundle such that it increases the product of utilities just by this local adjustment. That's the reason.
Okay.
Okay.
Yeah, okay. I'm just saying that a priori, if you had said, okay, maybe 2 is the right number or 3 is the right number, but somehow 1 seems to work, yeah. But
yeah, okay, so 1 is actually, if you just want an EF1 allocation, it's not that hard to see because, okay, so let's talk about this slide. I guess I'll try to address that question. So if you just want EF1, like intuitive techniques like round robin will also give you, if you're looking at additive valuations, like in every round, every agent, so there is a set of unallocated goods, and in every round, every agent picks his favorite unallocated good, okay? So you can even show that such an approach is an EF1 approach. Or an approach like envy cycle elimination, which is a generalization of the following approach. So assume that all agents have identical valuations, okay? All of them have identical valuations, and you iteratively pick one of the unallocated goods, and you allocate it to the agent whose valuation is the least. Now, clearly, following the removal of this good that you have allocated, nobody's going to envy this because this is the agent with the least valuation, right? And you just keep doing this again and again. If all agents have identical valuations, this is going to give you EF1. Envy cycle elimination is kind of a generalization of this, where you don't have an ordering among the agents just based on the valuation function, but you have an ordering based on envy, and you have this concept of envy graph. But there are much more intuitive and natural techniques which will also lead you to this fairness notion. And an alternative way to get it is also to generalize the techniques from the divisible good setting, which will also give you this fairness with efficiency.
Mm-hmm.
Okay, so Nash welfare maximization will give you EF1 with efficiency. And unfortunately, this is not where the story of discrete fair division ends. Quite the contrary, this is where it begins, because EF1 is not the best relaxation of EF, right? We can come up with definitions which are better than EF1. Like, just to give you an example why sometimes EF1 allocations can be unsatisfactory. So consider the following setting where you have to divide a house, bag, and a shoe, and consider this allocation where you give the house and the bag to the first agent and you give the shoe to the second agent. This is an EF1 allocation, right? Because agent 2 says that, okay, the agent 1 has a house and a bag, sure, I envy him significantly. But the moment I remove the house from his bundle, then he's left with a bag, and I don't envy that anymore. So in particular, the pitfall of EF1 is that you are allowed to remove any good from the other agent's bundle. In particular, you can remove the most valuable good according to you from the other agent's bundle. But the most valuable good might be the reason for such a huge envy to exist in the first place. So this can result in some unsatisfactory allocations at times. So as a result, we need to look at stronger definitions. And one stronger definition, a natural stronger definition, is to flip the quantifier. So now we say that look at all pairs of agents I and I prime. The envy should disappear following the removal of any good from I prime's bundle. Not just there exists some good following removal of which the envy should disappear. No matter which good I remove from I prime's bundle, the envy should disappear.
Right.
In particular, even after removing the least valuable good instead of the most valuable good, the envy should disappear in the context of additive valuations. And just to make it clear what this will give you in this setting, so this will so clearly this allocation will not satisfy EFX. So EFX, because the valuation for the shoe is significantly less than the valuation for the house, which is valuation for X1's bundle following the removal of a bag. So even after removing a bag, there's a huge skew in the valuations. Skew in the valuations for the bundle. So this will not satisfy any approximations of EFX itself. So an EFX allocation will force you to give the house to the first agent and the bag and the shoe to the other agent. Clearly, you might still say that there's a huge skew in envy, but hey, this is like a lottery working here because you have one good which is super valuable than the others. So you can do some randomization and get some ex ante guarantees, but as of now, I'm just saying that this is unavoidable, because if you just say you only had the house and no other goods, one of the agents will get the house, right? So this is in a way the closest analog of envy-freeness in the context of indivisible goods. So is the definition of EFX clear? Okay. So now, we ask the same question, that no matter how many agents, how many goods, and whatever valuation functions we have, can we always find a partition which satisfies this property? And unfortunately, we do not know it yet. And this is considered one of the most important problems in discrete fair division. And just to show you how embarrassing our understanding is, let me just, okay, so before that, I'll just tell you why it is so hard. Because if you try to extend the techniques from divisible setting, or if you try to come up with natural techniques or round robin or envy cycle elimination, you'll always end up at EF1. So if you want to go beyond EF1 to, let's say, EFX, then we need newer techniques. And as I said, so let me tell you what our understanding is as of the moment. So when all agents have identical valuation functions, okay, then we know that EFX allocations exist. When there are just two agents with general valuation functions, then also we know that EFX allocations exist. And this will follow from the protocol that I showed you in the very first slide, the cut and choose protocol. And when there are three agents with additive valuations, so additive valuations are the extension of like linear valuations in the discrete setting, where valuation on a particular set is sum of valuations of the items of the set. This is also the most well-studied class of valuation functions. When there are three agents with additive valuations, this would exist, and this is one of our results. And it is a very involved result, and I'll be talking about, and it's not an easy proof. It's a very complicated, technically involved proof, and I'll be mentioning briefly the difficulties that we overcome later in the slides. But starting from 4 or more agents, the question is open. So let me make it a little bit more clear. So what is open? So 4 agents, even with additive valuations, we do not know whether an EFX, we do not know, we don't have a proof that EFX allocations exist. For 4 agents with general monotone valuations, only assumption on valuation functions is monotonicity. We do not have a counterexample showing that EFX does not exist. Okay, so it's very much open.
So is your proof constructive, or do you give an efficient algorithm, or is this?
Our proof is constructive, but the algorithm would be pseudo-polynomial, which can be turned into an FP task. But yeah, we'll tell you the results right now. So now I would tell you what are the main results that I would be talking about here.
Bhaskar, we're sort of halfway in the talk.
Yeah, thanks, Kavita. Yeah. So the first result that I would be showing you is that even when agents have very general valuation functions, when we are making no assumption about the valuation functions, we can find an EFX allocation with almost all the goods allocated. Okay, some of the goods I will not allocate. Just a very small fraction of the goods I will not allocate. The remainder I'm going to allocate, and I'm going to show that whatever I allocate it fairly. Now, since our goal is to find fair and efficient allocations, I would show you how to get this guarantee with some efficiency guarantees also. Then I would show you that when there are only 3 agents, how can we get a complete allocation, meaning that there is no set of goods left unallocated. You might ask me like why this is interesting, like 3 agents, 4 agents. So first of all, it's interesting because it's a fundamental question, and secondly, if you look at discrete fair division instances, these typically involve small number of agents. Say in a divorce settlement, there are just 2 people involved. When you're settling an inheritance, there might be the number of people involved or the number of children, which is still like 3, 4, 5, right? When you're dissolving partnerships, the number of partners can be less. So usually the number of agents is small and the number of goods to be divided is large. So therefore, even these small instances are important from a practical standpoint. Okay, and lastly, I will show you that if you want to improve guarantees for EFX allocations, then I'm going to show you a connection to a problem in extremal graph theory. So if you do not like this setting with agents, valuations, and all of this thing, I'm going to give you a combinatorial graph theoretic problem. I'm going to show you how guarantees there will help you improve the guarantees in EFX. So this would be what I would be showing you for the rest of the talk. Okay. So let's start with the first result, the EFX allocations with almost all goods allocated. So here we show that, well, there exists a partition of the goods set into n+1 bundles, not just n bundles, rather n+1 bundles, x1 up to xn, and the pool of unallocated goods P. So x1 up to xn is allocated to the agents, the set P is unallocated. If I make the state such that whatever is allocated satisfies EFX. So if I make this statement in itself, it's uninteresting, right? Because I can put the entire set of goods to P and not allocate anything, which is trivially envy-free. So for this to make sense, I need to give you qualitative and quantitative bound on the set of unallocated goods. So here in this slide, I say that, well, the set of goods that are unallocated are not that valuable, meaning that no agent envies the set of goods that are unallocated. Every agent is at least as happy with their bundle as they are with the set of goods that are unallocated. And less than n-1 goods go to charity. So n is the number of agents, which is significantly less than the number of goods. And as I said, so for 4 agents, even with additive, I told you a slide ago that this problem is open, right? So corollary of this theorem would say that if I remove 3 not so valuable goods, the remainder of the goods, I can allocate it among the 4 agents, even when agents have general valuations such that the allocation is EFX. An alternative corollary of this result is that if you have one agent who is beyond envy, meaning that who doesn't care about envy at all, who doesn't care, who doesn't distinguish between the bundles at all. So his valuation for all bundles is the same. Then again, EFX allocations exist. right? You just, whatever is going to charity, you can allocate. So whatever is unallocated, you can allocate it to this agent. Nobody's going to envy this agent. This agent is not going to envy anyone else because he's beyond envy. There's another corollary. So if you have just one agent whose valuation is like the same for all bundles, then EFX allocations exist even when other agents have arbitrary general monotone valuations. It's a consequence of this theorem. Is the theorem statement clear?
So,
Okay.
Bhaskar,
Yeah.
we could always add God to any problem, right? And assume that God values everything equally. So if you add an extra agent and assume that he, as you're saying, he's beyond envy, then every problem is solved.
Then every problem is solved, yes.
But why should the rest of the agents bicker because I added one more agent?
I mean, yeah, I mean, I actually don't have an answer. I mean, so that's why you say that this is essentially EFX with charity, right? So whatever is unallocated is what is going to charity, and a few amount is actually going to charity. And I don't know. I mean, so I mean, if you want to settle the existence of EFX, I guess it's interesting to see what happens if you want to allocate all the goods, for instance. I mean, there would be a lot of interesting properties that you would like to see whether they're satisfied. Like you would see, as I described the algorithm here, you would see some interesting mathematical questions that come up if I insist that all the goods need to be allocated to the agents. But from a practical standpoint, I agree that I guess this result should give you most of the, interesting results, yeah.
And I guess, Rahul, one way to answer your question would be it would only solve the problem if you believe in God. If you don't believe in God, then maybe you're just throwing away the good side. But I'll stay out of this discussion.
Yeah. Okay, so for now, I would just show to you the proof of the first two statements such that you also get a feel of the algorithms so most of the algorithms would have the same algorithmic structure, but the subroutines that we would be using in this algorithmic structure would just be a little bit more involved.
Hey, Bhaskar, so just a quick question. So the P, while the inequality stands, so like VIXI is at least VIP, like P could have significant social welfare. It's just that, like, for example, like each good in P was valued by a different agent and had a high value. So the first good had value like equal to V1 X1 and only the first good. The second good in P had value V2 X2 and only. So in particular, like P overall could have significant social welfare. So you are being rather religious if you.
Yeah, I mean, if agents valuations are like that, like for instance, every agent likes just two goods.
Right.
And like say you give every agent just one good and all the goods that each of them like, you just throw them into the pool. But again, like when you say social welfare, it's not quite clear to me because you have heterogeneous valuations here, right? So if you want to fix the welfare.
Optimal, like if like P as such could have been distributed with a grade. So all I'm saying is like a point. It's like saying like in a divorce settlement, everyone, like 1/3 of the property goes to a temple. I think many people will contest to that.
Mm-hmm. Yeah, I mean, you would see that we can get these guarantees with half Nash welfare.
Right.
I mean, as I would show later. So it is possible that maybe like 50% of the goods, I mean, somebody values the set P, I mean, 50% of the total welfare, you know?
Right.
So that could happen, yes. It could still happen. But like if you look from every agent's perspective, because the problem that we are considering is from every agent's perspective, right? Like envy-freeness. So from every agent's perspective, it's still not that much.
Got it.
This is what I'm trying to say. Yeah. Okay. Great question. So let me now tell you the algorithmic framework here. So always we would maintain a partial EFX allocation, meaning that an EFX allocation where not all goods are allocated. And as long as there is an agent that finds the pool of unallocated goods valuable, we will get a better partial EFX allocation, meaning that a partial EFX allocation where every agent is every agent is at least as happy as they were before, with some agents being strictly happier, meaning that the valuation vector that you're going to get in X prime Pareto dominates the valuation vector of X. Okay. And this would actually show convergence because you can always assume integral valuations, and this would eventually converge because the valuations are integral and upper bounded. And when it converges, you would see that there is no agent who strictly envies the pool. And thereby you get the guarantees in the first two statements of the theorem because we are maintaining a partial EFX allocation and no agent would envy the pool. So this would be the algorithmic structure. So I just need to show to you here that how can we transform a partial allocation to a better partial allocation if this precondition is satisfied. So for this, I would introduce a very crucial concept, which is very crucially used in all the result, which is the concept of a most envious agent. And you would see that it's pretty natural. So given an allocation X, say x1, x2 up to xn, and a subset, say any set, say S, and let's say we're given an agent I, clearly agent I envies the set S, right? Because VI of Xi is strictly less than VI of S. And now the thing is, I want to quantify this envy. How much do you envy? One naive way of doing it is like, just look at the difference, like VI of S minus VI of Xi. But since the underlying notion of fairness is the existence of envy following the removal of goods, a more natural way to look at it is okay, there are 5 goods in S, and all 5 goods put together is more valuable to me than my current bundle. However, if you look at it, just 2 goods from S suffices for me to envy this set. Okay, so I define Zi to be the smallest subset of S that agent I still envies. Smaller the size of this subset, I would say greater is the envy for this agent. Greater is the envy that the agent has for the set. Just to explain this to you, with a small example. So for every agent, we define this quantity kappa xi comma x, which is the size of the smallest subset of S that agent I still envies. And the one with the smallest value of kappa xi comma S are the most envious agents, like I said. So a very simple example, let's say you have 3 agents and the set S. For agent 1, the size of Z1 is 2, the size of Z2 is 3, and the size of Z3 is 4. And clearly, the most envious agent is agent 1 here, because agent 1 just 2 goods from S suffices for agent 1 to envy. Now, what is the advantage of this definition? So observe crucially that nobody envies Z1 up to 1 good. Why? Because for agent 2 to envy any subset of S, it needs to be of size at least 3 by definition of Z2. For agent 3 to envy any subset of S, it needs to be of size at least 4. But Z1 is of size at least 2. It's of the smallest size by definition. As a result, nobody would envy Z1 following the removal of a good. So there could be ties. There could be another agent who also envies Z1. But then following the removal of this good, this envy would disappear. And more importantly, this is a set which the agent values more than its current bundle. So I have found a set which an agent values more than its current bundle, and which all other agents would be fine if I allocate this bundle to this agent. So let me make this statement a little clear. So imagine that we are in this situation where we have a partial EFX allocation, and there are these agents 1, 3, 4, and 11 who envy the pool. Then I ask, okay, who among you envies the pool the most? Find the most envious agent by the definition that I just said. You give this agent the pool of unallocated goods, and you throw whatever this agent has back into the pool. As a result, all the red edges would now be redirected towards this agent. But then I say that I don't need to give this agent the entire set of unallocated goods. I just need to give him the bare minimum with which I can still improve his valuation, and then throw the rest back into the pool. So with this kind of an operation, agent 3's valuation strictly improves, while all the other agents retain their previous bundle. So I've got a valuation vector which Pareto dominates the previous valuation vector. And it is EFX because nobody envies Z3 following the removal of any good, because agent 3 was the most envious agent. Okay, so if you just keep applying this update rule, then you would reach at the first 2 statements of the theorem. All right, and now what we show for getting all the 3 statements of the theorem is a similar update rule.
Bhaskar, the third statement was that the size of the leftover pool is no more than n. Is that okay?
Yes. So it's, and to get the third statement of the theorem also, you just need to find an update rule which also does the same. Like it gives you a better partial EFX allocation when there are more than n unallocated goods. And this update rules would be more involved, and I would skip them. But you get the idea. I guess you again use the concept of a most envious agent and you come up with, say, reallocation rules. Okay, and now the goal is that, recall that we said that we want to find all our guarantees with efficiency, right? So what I've told you gives some EFX guarantees. It does not give you any efficiency guarantees. Yeah.
So why are you stuck at n and not any other number? Can you give some intuition? How is it related to the number of agents?
Because so what happens is that, so the intuition to why, if it is larger than n, you can do an update, is that so it's actually not n, it's the number of sources in the NV graph to what we call. So it works as the follows, that if I try to allocate a good to an agent that nobody envies, and if some other agent envies this agent right now, then I try to give that agent some other good. Okay, like I try to give G1 to an agent that nobody envies. And now there is an agent who says that, no, I mean, the moment you give this guy G1, I'm going to be the most envious agent. So then what you do is, like, you take another good G2 from the pool and then you try to give it to this agent. And then you say, okay, fine, I'm giving you G2. Can you be satisfied? He may say no, he may say yes. If he says no, it's easy to deal with. If he says yes, there could still be some other agent who would envy this. So then you take another good from the pool. So the number of goods that you pick is the number of agents that nobody envies. So, and this number of agents that nobody envies could be as large as n. That's the bound. So actually the bound is the number of agents in your partial EFX allocation that nobody envies. I mean, alternatively, you could also think of it as like taking one for each agent, like, in a way. Shall I proceed then with the efficiency notions? Yeah. Okay. So now, as I said, so we want to get all these fairness guarantees with efficiency guarantees, right? So recall that our notion of efficiency was that of Pareto optimality. But unfortunately, there are trivial instances where no EFX allocations is Pareto optimal. So EFX allocation is not compatible with Pareto optimality. So we look at a non-binary measure of efficiency. And I said that, well, I mean, at the very beginning slide, I said that a very nice measure of welfare, which is compatible with fairness, is that of Nash welfare. You look at the product of valuations and you kind of get an estimate of how much welfare your allocation achieves, how much non-wastefulness is there in your allocation. So now our goal is to find EFX allocations with high Nash welfare. And Nash welfare maximization in itself has been extensively studied. I mean, this problem is APX hard. And it has and there are constant factor approximations when there are additive valuations, and like n log n approximation when there is submodular, and order m when there are subadditive valuations. And what we show is that if you just modify the first step of our algorithm, so our algorithm kickstarts with an arbitrary partial EFX allocation, which is essentially the empty set, because the empty set is trivially partially EFX. It's envy-free. But if you kickstart the algorithm with a clever partial EFX allocation, and then you rerun the same algorithm, then you will get an EFX allocation with all the guarantees I said earlier, but with high Nash welfare. So that also speaks about the robustness of this algorithm. In particular, you get constant factor approximation in polynomial time when agents have additive valuations, and you get an order n approximation for Nash welfare when agents have subadditive valuations. And in fact, I mean, so the n approximation for subadditive valuations is also found by Siddharth, Umang, and Krishna and Sundaram. And in the same paper, they also show that it is while you're restricting yourself to value queries, you cannot do better. You cannot do sublinear approximation with polynomial many value queries. So this is as tight an approximation that you can get, but you can get this with your fairness measure. You can get it with the EFX guarantees that I said earlier. So just to put it into perspective, so we get almost optimal bounds for additive, like 2 times e to the 1 over e. And we improve the state of the art for subadditive and submodular, and we get all of these efficiency guarantees with EFX guarantees. And I would like to remark that quite recently, there is a paper, very good paper by Jan Vondrak and Lee, who showed that you can obtain constant factor approximation to Nash welfare when agents have submodular valuations. And it's a pretty good paper, and I highly encourage you to check it out also.
So Bhaskar, can I ask a question?
Yeah.
So for the items that you do allocate, are you Pareto optimal with respect to those?
Not necessarily, no. Because I mean, you could end up so you could end up allocating all the items also. I mean, you can, so for instance, the instance that Cloudcraft Garden shows, for instance, where EFX does not is not compatible with Pareto optimality. If you run our algorithm on that instance, it will allocate all the goods. So clearly, it will not give you Pareto optimality there. And I don't find an easy way to modify it such that you can get Pareto optimality. I can tell you a few more things, like if actually EFX, like if you want, say, to get certain EFX guarantees with, like, you cannot get full EFX with Pareto optimality, but if you want to get certain relaxations of EFX with Pareto optimality, it would have interesting consequences to the existence of EFX allocations itself. But maybe I can cover this after the talk. This would be like, yeah.
Thanks.
Yeah. So, and I would just like to mention that with this approach, we can also get an N approximation for a broad range of welfare functions. It's not just the Nash welfare, but the p-mean welfare, which is the pth norm of the valuation vector, and for subadditive valuations. And each of, like, some of them have been studied independently. Like p equals to -infinity corresponds to this max-min welfare, p equals to 0 corresponds to the Nash welfare, and p equals to 1 corresponds to social welfare. So the algorithm that I showed you earlier gives you EFX guarantee with an N approximation for all of these setting when agents have subadditive valuations. Okay, so now I want to focus on how
Bhaskar, what is that? Sorry, what is the clever allocation you begin with?
So for additive valuations, what you can do is you can look at a good approximation of Nash welfare, and you can kind of contract it to a partial EFX allocation by tracing it back, and then run the algorithm from there again. For subadditive, it's a little bit more involved. So the intuition is that if you have an envy-free allocation, then you have an N approximation, right? Because VIXI is greater than or equals to VIXJ, and you just sum it up, you get 1/n times evaluation for the entire set. If you have an EFX allocation where every bundle is of size 2, then also you get an N approximation because you have VIXI greater than or equals to 1/2 times VIFXJ. And you again get an N approximation. So the only problematic case is when there are certain singleton bundles. But there can be at most N such bundles. There can be N such goods which can be problematic. So you cleverly start with a matching at the beginning, and then you run our algorithm. So you start with a clever matching, and then you run our algorithm, and this will give you an order N approximation when agents have subadditive valuations.
Thanks.
Yeah. Okay, so so now let me talk about complete EFX allocations for 3 agents. And as a corollary of the first theorem, we know that they're all already, it gives you that there is a partial EFX allocation with at most 2 unallocated goods. So our goal is to just get rid of these 2 unallocated goods, which may seem to be not that difficult apparently, but unfortunately it is. I mean, getting rid of these 2 goods is very tedious. And when agents have additive valuations, we show that we can indeed do this. And the proof is very technical. It spans over 15 pages. Maybe it's not the most elegant proof, but it will tell you a lot about the structure of the partial EFX allocation when the update rules that you applied earlier are no longer applicable. Okay, so let me just tell you what is the main difficulty. So let's say we want to generalize the previous approach, but with a stronger precondition, saying that, well, if there are any set of unallocated goods, then we try to get a partial EFX allocation Pareto dominating the previous allocation. Can we do this? Unfortunately, this is not possible. In particular, I can show you an instance with an unallocated good G, and a partial EFX allocation X and an unallocated good G, where no complete EFX allocation can Pareto dominate this partial EFX allocation. Meaning that if you want to allocate this good and still maintain EFX, then one of the agent's valuations will strictly decrease. Therefore, you cannot use the potential, like improvement on the Pareto front of the valuation vector that we have been using so far. So here's an example. This is the example with 3 agents and 7 goods. We have an allocation of the first 6 goods, which you can verify to be EFX. The 7th good is unallocated. And if you want to allocate the 7th good one of the agent's valuations will be strictly less. Either A1 will be strictly less than 16, or A2 will be strictly less than 15, or A3 will be strictly less than 10. This is the bottleneck. And how do we overcome this bottleneck? Well, in this example itself, we observe, like this is what I said, like in all final allocations, at least one of the agent's valuation strictly decreases. But what we observe is that, okay, here is a complete EFX allocation where agents 1 and 3 are strictly better off. They're 19 and 11, while 2 is worse off. Here is another EFX allocation where agents 1 and 2 are strictly better off, but 3 is worse off. In particular, for each I, there is a complete EFX allocation where agent I in particular is better off. And what we show in the paper is that this is true in general. Like whenever you have one unallocated good, there exists a complete EFX, there exists EFX allocations where each agent is better off. Like there exists, for every agent, there is an EFX allocation where this agent in particular is better off. And now the question is, can we leverage this? It turns out we can. We just relabel the agents as A, B, and C and look at this potential. We change our potential. The potential is this lexicographic, like is this vector, which has the first component as a valuation of A, the second as a valuation of B, and the third as a valuation of C. And notice that if x prime Pareto dominates x, then phi of x prime is lexicographically larger than phi of x. So all the rules that I showed you earlier, I mean, you can still apply them. And let's say what I said earlier is true, that given any partial allocation, an unallocated good, there exists another partial EFX allocation x prime where agent A in particular is better off. Maybe B and C are worse off, but agent A's valuation I can increase. That means that I can find a partial EFX allocation x prime where phi of x prime is lexicographically larger than phi of x. And then again, since this potential is also bounded and valuation functions are integral, this would finally show you the existence of EFX when there are 3 agents with additive valuations. But coming up with these update rules to show you that you can find an allocation where agent A is better is very tedious and very technical. And I'm not covering that as a part of this talk.
This need not be unique, right? Or does it?
Unique as in?
Well, EFX exists. Does it have to be unique, or can it be multiple solutions?
There can be multiple solutions, yeah. There can be, like just in the previous slide, I showed you several complete EFX allocations for an instance, right? There can be several EFX allocations, yeah. Okay, so finally, Kavita, can I have like 7 or 8 more minutes? I mean, just
oh yes, of course.
Yeah, okay, thanks a lot. Okay, so finally, I will show you how this problem, I mean, I'm trying to encode the hardness of this problem in, say, a graph theoretic sense, such that, I mean, I guess it would be more accessible to a broader audience also. So in a way, our goal right now is to reduce the charity. So our previous result shows that EFX allocations exist with where there are at most n-1 goods going to charity, right? Now let's say that a systematic way to approach this problem is to reduce this n-1 gradually. So the question asked that, can we find EFX allocations with sublinear charity? And we show that indeed we can. So there's a little bit of cheating here because we say we find approximate EFX, but just ignore that for now. So you find, say, 1 minus epsilon EFX, which is an almost EFX allocation, with the number of goods unallocated being n over epsilon raised to 4 over 5. So it's sublinear here. And the main takeaway is that we can show a connection between finding by improving the sublinear improving the charity, we can connect it to a problem in extremal graph theory. So what is this? What is this connection? So I'm going to define a number which might be a mouthful on this slide, but just bear with me because I'll explain it graphically in the upcoming slides. So we define this number R of D, which we call the rainbow cycle number. So given any integer D, R of D is the largest K, such that you have a K-partite graph G. So V1, V2 up to Vk are the K independent parts. And each part has at most D vertices. So I'm going to give you certain conditions that this K-partite graph should satisfy. And now my final question would be, how large can this graph be? Or like, how many parts can this graph have? And I'll show you how that relates to EFX. So, okay, so each part has at most D vertices. You take any 2 parts here, Vi and Vj. Each vertex in Vi has an incoming edge from a vertex in Vj and vice versa. Okay, it's a directed graph. Each part has d vertices, and like the induced bipartite graph between any two vertices is cyclic. And this is the most important condition. There exists no cycle that visits each part at most once. Meaning that if this k-partite graph contains any cycle, then this cycle must contain two vertices from some part. It cannot be that this cycle contains at most one vertex from every part. So whatever part it visits, it contains just one vertex of it. This is an illegal cycle. So satisfying these constraints, how large can K be? So that is what we call R of D. Why is this why is this rainbow cycle? Because you can kind of color the edges outgoing from a particular part with one color, and the question is this, and the graph should not admit a multicolor cycle. That's what this number says. So how does this relate to EFX with charity? So we show that any upper bound on R of D will give you some. If you can just show that this number is finite, you will already get sublinear charity. In particular, if you can find better upper bounds, then you can get better bounds on charity. So let me just explain this number a little bit, because it was a mouthful from the previous slide. Like this number is not a meaningless number. It is indeed bounded. So let's consider the value of R for small values of D. So let's consider D equals 1. So, okay, I can definitely have one part containing exactly one vertex, because each part can have at most one vertex, like I said. So there's one part containing one vertex. Can I have another part? Well, if you have another part containing one vertex, A2, the second condition dictates that A2 should have an incoming edge from A1, and A1 should have an incoming edge from A2, right? Because these are the only vertices in the two parts, and this part can't have more vertices because each part can have at most one vertex. And this is an illegal cycle, because here's a cycle which visits each part at most once. So when D equals to 1, R of 1, you cannot have more than two parts. So R of 1 is at most 1. Now let's look at R of 2. So let's say you have two parts, and say part 1 has A1 and part 2 has B1. So let's say B1 in A1 has an incoming edge from A1. Now A1 should have an incoming edge from some vertex in B2, and it cannot be from B1, because otherwise you again get an illegal 2 cycle. So it should be some other vertex, right, from B2 in B2. Now, same goes for B2. So B2 cannot have an incoming edge from A1, so it should have an incoming edge from some other vertex, A2. Now notice that these parts can't have any more vertices, because each part can have at most 2 vertices. So A2 should have an incoming edge from B1. So yeah, this is okay. It has a cycle, which is A1, B1, A2, B2, A1. But this is a cycle which has 2 vertices from each part. So this is a valid cycle. So yes, R of 2 can indeed be 2, but can it be more than 2? Can it be 3? So if it is 3, then you see that the structure of this bipartite graph between the two parts is forced. There is no, whatever is the bipartite graph between V2 and V3, it is going to be isomorphic to that between V1 and V2. So you're going to have a similar structure. And between V1 and V3, you will have a similar structure, which would mean that either you have an edge from A1 to C1, in which case you have a 3 cycle like this, which visits each part at most once, or you have an edge from C1 to A1, in which case you have a 3 cycle which visits each part at most once like this. So if like this, you can also show that R of 2 is at most 2. And in what we show is R of D is indeed bounded, finite, and polynomial. It's D to the 4. And this implies the existence of approximate EFX with n over epsilon to 4/5 charity. We suspect that R of D is linear. We didn't prove it in the paper, but we suspect that R of D is linear. And this would imply the existence of 1 minus epsilon EFX with square root n over epsilon charity. So the main takeaway is that if you want to improve the bounds on charity, then you can just work with this graph theoretic framework. That is the main takeaway from the result. Okay, so that concludes most of the results that I wanted to cover, and I would like to say a few points for the future direction. So the biggest open problem is to settle the existence of EFX allocations for 4 or more agents. An immediate, like a step towards this direction is to find tighter bounds on this rainbow cycle number, which I believe is of independent interest in itself, but it can also give you like better bounds on EFX allocations. And now the entire talk that I had was on goods setting. Nothing is known for EFX. By nothing, I mean most of the results that we saw so far are not known for EFX allocations when you consider bads. So that's a whole new area which is actually open and would be interesting to explore. The second thing is, although most of the algorithms that I showed you, most of the proofs that I showed you are algorithmic, the algorithms are not polynomial time, they are pseudo polynomial time. And unfortunately, we do not know any polynomial time algorithms, neither any hardness results, even for the settings where we know that EFX allocations should exist. And even when agents have additive valuations. Or in general, complexity of discrete fair division where agents have linear preferences. There are other problems like something Siddharth and Rohit have worked explicitly on EF1 plus PO. So the complexity of these problems are also unsettled. I mean, it's a very interesting domain because right now most of the work is towards settling the existential questions, but the whole domain of, the complexity of these results is actually open. And finally, you can also look at other related settings, like for instance, asymmetric settings. So far the setting that I told you, all agents are equally entitled. So there could be settings where some agents are more entitled than the others. And what happens in such settings? I mean, how would you, there are natural ways to generalize these notions of EF1 and EFX, but what can you say about existential and computational results there? Similarly, the setting I described here is all one-sided, where you just want to be fair to the agents, but several of the real life settings are two-sided. Like for instance, when you want to match, say, drivers to riders or hosts to, like Airbnb hosts to guests, or say reviewers to papers, all of these, you require fairness on two sides. So what can you say? And more importantly, for the platforms, there are a lot of electronic platforms that can employ these fairness protocols, like Airbnb, Lyft, or Uber, or EasyChair. These are all centralized platforms which can actually employ these fair division protocols in contrast to the setting or to the one-sided fairness that I discussed. So it might be more interesting to look at that. And in general, I guess applications of the techniques that I said, whichever in settings which involves a set of agents and collective decision making, I guess it would be interesting to see. So thanks a lot. I guess I went a little bit over time, but I hope you like the talk, and I would be open for some questions now.
Thank you for a really nice talk, Bhaskar.
Bhaskar, did you define? Did you define 1 minus epsilon EFX and also extremal graph theory? Some of us don't know these things.
Okay, thanks. Yeah, maybe I shouldn't make that assumption. So 1 minus epsilon EFX, yeah. So I had it in the definition, but I guess I quickly skimmed over it because I just wanted to say it's like an approximate EFX. Because so what happens is VIFX. So in EFX, what do you have? VIFXi is greater than or equals to VIFXi prime minus G, right? So here you just scale it with 1 minus epsilon. That's it. So that's 1 minus epsilon EFX.
Okay.
So the best EFX for additive, the best 1 minus epsilon, which is known to exist, like complete EFX, to the best of my knowledge, it's the golden ratio, like 5 minus 1 for additive evaluations. But this result, for instance, it gives you sublinear charity, and it gives you an approximation of 1 minus epsilon for any epsilon.
And do you assume the valuations are additive here?
Yes, the valuations are additive here. I mean, the only result which like holds for general valuations is the first results with n-1 charity. The one with efficiency guarantees we can only give up to sub-additive valuations, but constant factor efficiency we can only give for additive. And the rest, like EFX for 3 agents, EFX with sublinear charity, all of these results hold only in the additive setting.
So do you believe these would hold for all monotone valuations?
I actually don't know. I mean, it's very hard to prove stuff. I mean, I would definitely say that one would. I mean, the proof techniques definitely don't extend, and I would expect that one requires a completely different set of tools to deal with more general kind of valuation functions.
So, what's extremal graph theory?
Yeah, so extremal graph theory are like questions in graph theory where I tell you that, okay, there is this kind of graphs which satisfy certain kinds of properties, and you want to know how large these graphs can be, in a way.
Thanks.
Or like, I mean, this is a very generic way of saying it, yeah. But yeah.
So Bhaskar, so suppose the rainbow cycle bound was linear. What would that translate to in terms of the charity size?
Square root n.
Square root. I see.
Yeah.
Okay.
So
okay.
What it actually translates to is you look at the function d times r of d. So let's call this h of d. so the speed, the improvement you get in charity is H inverse n. So you get n divided by H inverse n charity. So like if R of d is d, then H of d is d squared. So H inverse is square root d. So you get n divided by square root n. So you get square root n charity.
I see. Okay.
So any questions?
Is this rainbow cycle number something that was studied earlier?
Not quite. Yeah, no.
Okay. Okay. And the other thing is, I mean, like, I understand that for the charity problem, this will give us better bounds. There is, do you think there is a black box reduction from reduced charity to, from, EFX to charity to EFX?
EFX to charity to EFX.
Like in your case, you used certain tools and structures to go from the case where you had just two items unallocated to get a full EFX allocation. Do you think something like that might be more generally doable?
No, I don't think so.
Okay.
I don't think so at all, because here, for instance, for EFX for 3 agents itself, the thing is that it's not even, so what makes this problem so weird is a sense that, I'm not even sure whether, say, like if let's say you can show that EFX does not exist for 4 agents. Is it clear? Can you immediately come up with an example where you say that EFX does not exist for 5 agents? I'm not so sure, because for instance, this result, the corollary of this result tells you that if you have an agent, like if you try to add something like a dummy agent here, then EFX will always exist. So you crucially need to use the valuation of the 5th agent. So any kind of reductions, like EFX, like to smaller cases, I'm not quite sure, because I'm not quite sure about the monotonicity of this existence. Like if it exists for smaller instances, I'm not so sure whether, most likely it is true, but I'm not so sure how to prove that if it doesn't exist for a smaller instance, it would exist for a larger instance.
Okay.
Because you have to crucially use the valuation structure of the extra agent that you add, or you have to crucially use the valuation that the agents have for the extra good that you have, say, introduced. So it plays a significant role. It can change the head and tail of, say, feasible EFX allocations itself. Yeah.
Right. Okay. Thanks.
Hey, quick question, Bhaskar. So, do you think the result that you have on the screen or the other ones, like the sublinear charity, do they translate to give something for notions that are between EF1 and EFX?
I'm just aware of this notion, right? EFR, like where you randomly pick.
Right. Yeah. So.
I'm not so sure. I guess, yeah, because I guess the result for EFR, I think, yeah, maybe we can say more stuff about, like, we can say, so I assume your question is, can we give better guarantees for notions which are between EF1 and EFX, right? Because whatever guarantees we have for EFX, we will have those guarantees for anything between EF1 and EFX.
But yeah, so maybe like no charity and you somehow.
Right. So that's a very good question. I haven't thought about it, but for EFR, I think I read the paper once, and my gut feeling tells that maybe we should be able to get better results there. Yeah.
Okay. And the extremal connection you have, that's a one-way street, in the sense that it might be that R of D is superlinear and still you don't have the connection is that this particular method or template of iterative extension works if this happens.
Right. Yeah. It's one way.
So there could be a complete,
Yeah. So for instance, I think a better question would be to, like, if you look at how we do this reduction, like to this extremal graph theory, it involves this concept of what is called group champion graphs, which are generalizations of champion graphs, and like which is a combination of champion graphs and envy graphs. But I think a bigger thing is so that if you look at the group champion graphs, it looks like a very natural extension of champion graphs. So maybe we can actually think about more complicated or more sophisticated tools with which you can get even less than square root in charity, because R of D is definitely D. I mean, we can show a lower bound. So with that kind of an approach, you cannot improve it beyond square root n. Although it's not clear to me whether EFX allocations with less than square root n charity exist in the first place. But if you want to show, then perhaps an approach would be to come up with more sophisticated tools than, say, group champion graphs.
And so, like, again, one sort of maybe a specific question and a vague one after that. So the specific question is, do you think like this, like linear charity also holds for like beyond additive valuations?
Sublinear charity or linear charity?
Like n-1 result. Is that, I think that's for additive.
No, n-1 holds for general valuations.
Okay, yeah. So yes, you're only looking at the minimum GI. So like, yeah, final. So I guess like the totality argument in this is like a potential argument, right? Like this, like either your phi, the lexicographic, or the parity. Like, is there somewhere that like a parity argument is also built in? Because that's interesting, because EF1 existence is a parity, like Lipton, for example, is a parity argument.
Yeah, I mean, that I believe that is the right thing to look at if you want to prove, like, so like these potential based arguments. I mean, I've tried them a lot, and quite frankly, I do not know of. I find it harder and harder to get, say, potential based arguments for more general case. So I believe that, yeah, I think the parity argument is the right thing to look at, especially if you want to deal with general valuations. I guess parity argument is the right thing to look at. But I'm not so sure about how to go about it. I mean, I think I told you also at some point in time that I have some insights where you can show that, well, like if I give you the assurance that, well, EFX allocations exist, then there is a way in which you can run a Lipton-like algorithm to reach that allocation, right? So we know EFX exists for 3 agents. So there is a way in which you can run Lipton algorithm, just Lipton algorithm. So which involves, like, you take a good, allocate it to an agent, and you decyclify. But the crux is, like, which good, which agent you allocate, and which kind of cycles you decyclify. This is the crux. This we don't know. So, but there is a way in which you can do this and still come to an EFX allocation. So I think we talked about this at some point in time, where I showed that you can trace it backwards. The thing is, I don't know how to make it forward. So maybe that could be one way to look at it. Like, maybe that should give you some insights for parity-based arguments, at least for the things that we know right now. I mean, that's also interesting from a complexity point of view, right? So you might get polynomial time, or if you can show like it's interesting, right? Because this kind of approaches shows membership in PLS. Like all these potential based arguments. Right. So it would be very interesting if one of them has a parity like argument also. So, I mean, yeah.
Okay, great. Thanks.
Kavita, you're muted.
Sorry, any more questions? So what's your guess, Bhaskar? Do EFX allocations always exist?
I actually don't know, Kavita. I mean, I would assume for general, it may not exist, but my fear is that it may not exist for a large n, like say 5, 6 or something. Yeah. I mean, that would make things very hard for like to settle this problem.
I remember Tim Ravgarden asked you the same question during your defense, and you gave the same answer. I wondered if you would become more hopeful now.
No, I don't think so. Yeah.
Can we run a massive, computational search to see there's a counterexample or something? Would that?
Yeah. So the drawback of such an approach is, like, even if you take, say, 3 agents and let's say 7 goods, like very, very small setting. So if you want to run so you need to find a way to break symmetries among the valuation functions. A lot of valuation functions you can just like that discard because they're very easy to deal with. But if you don't, and I don't know how to do that. I don't know a systematic way to break the symmetries. If you don't break symmetries, this is too big, even with 3 agents and 7 goods, right? Because there are 2 to the 7 possible subsets, right, of 7 goods. And a valuation function is just an ordering of these subsets. So you have 2 to the 7 factorial many valuation functions. And each agent can have one of these. So you have 2 to the 7 factorial cube instances on which you can brute force. So I mean, this number is already huge. So I mean, one needs to find systematic ways to break the symmetries. I mean, one can still, I think one can, I think I had discussed it with Siddharth at some point in time where we talked about like writing an LP based approach. But even there, I mean, you write an ILP, but it has something like, even with say 3 agents and 8-9 goods, there are like, I think 10,000 or 50,000 variables and a lot of constraints, and it's not clear. I mean, how to do. I mean, we need a much better understanding. We need to kind of kill a lot of valuation functions to kind of enumerate, and I don't know how to do that yet.
Okay, thank you. Thanks a lot, Bhaskar.